Hello everyone. So it's come to my attention that a lot of people are having difficulties in running the simulation for the heat and mass project. Excuse me. And I've talked to a few people, come to the conclusion that most of the problems that result in the simulation failure, and by simulation failure I mean like erroneous results and floating point exception, things like that. The root of the problem more often than not lies in the interface between the fluid region and the solid heat sink. Today I'm going to show a very simple technique to enclose your heat sink in the fluid using only space claim. This is very easy and should eliminate any inconsistencies in the interface between the solid and fluid that ultimately end up resulting in simulation failures more often than not. This is the culprit that most people run into, is the interface between the fluid and the solid. So here I have a new project open in Workbench in ANSYS, and looking at the scenario where somebody may have chosen to draw their heat sink in another CAD program, perhaps SolidWorks or any other CAD program. So I'm going to start by importing a geometry that's been saved as an IGES file. It's important if you're building your geometry in SolidWorks or another CAD program to save that geometry as a file as an IGES file. So first thing I'm going to do is import that IGES. This is just in the circumstance someone's built the geometry externally. If you've built it inside space claim, you won't need to import it, obviously. So we're just going to put a geometry here, just a single geometry project. If you're building your geometry in space claim, you can just double click the geometry and start building. I'm going to import an IGES when space claim opens. Okay, so we have space claim open. I'm going to go to File and click Open. I have a geometry in this folder called Example. I'm going to go down to here and select All Files, and there's my geometry. I'm going to open that in. This is not my geometry. A student has built this geometry. I'm just using this as an example. This should work. This technique I'm going to show will work with any geometry, as complicated or as simple as it is. So this one's reasonably complicated. We've got radius fins in here. It'd be very hard to manually make this void inside an air, which I've seen many people do, is manually extrude the air to conform to the heat sink in order to have the interface and the cutaway in the air to make room for the solid geometry. That's very not advisable to manually do that, and this technique, very simple technique, will take care of all of that for us and have no inconsistencies in the interface between the fluid and the solid heat sink. So I've imported the geometry. Next thing I'm going to do is make a plane and situate that plane above the heat sink. So we might select a plane. That's the XY. Yep, okay, so I've selected the XY. We'll make a plane on the XY. I'll select the plane and click Move. Right, so I want to move this plane in the Z direction. We can select this blue arrow. I might just zoom out a little bit first. Okay, let's say we want it about 110 mil might be enough. Just gonna, while I'm holding the mouse button down and not letting it go, if I let it go, it will put the plane in that position. So while I'm holding the mouse button down, I can type in 110, enter, puts the plane there for me. That's nice. Okay, So now I'm going to click on the plane. Well, let's click escape a couple of times. Click on the plane. I want to sketch to that plane. Go normal to the plane. I might go to the other side so I can see my heat sink in the background. Go normal to that and zoom in a little bit. Okay, for this example, I'm not going to be too accurate in the dimensions of my air. That's irrelevant. That's something you can work out, no problem at all. But what I might do here is just build a very simple block of air, paying no attention to the dimensionality of it for the example purpose only. Okay, so that seems okay for my block of air. You might want to make it a little bit wider than I've done here, but that's fine. We'll just make it that wide there for the purpose of showing this technique. That looks fine. We can now go back to 3D mode, and I'm going to select that drawing I just made. We want to select this here up to first, so we want to pull this sketch up to and no merge, so it doesn't merge my heatsink with this volume of air. So we've got up to and no merge. We can pull this sketch up to this surface. Click it. There we go. So we've got that done. But what we've ended up with now is a heatsink and a block of air that has no cutaway in it to make room for the heatsink. That's not what we want. So we're going to highlight both the solids. We have a solid block of air and a heatsink. We're going to now go up to it's prepare. Yep, prepare, and click this interference. So that interference has found that there's interference between the heatsink and the solid block of air that I've just created. And that's going to just fix that automatically for me. Click the tick button. Fixed one problem area. That's what we want. So now when we get rid of the solid, we got our heatsink. That's great. Get rid of the heatsink and put the solid in. We've got now a perfect interface between our heatsink and our block of air. It's done it all for us. So we know there's no inconsistencies, no overlaps, no gaps. And that's exactly what we want for running the simulation. Okay, so we've got our heatsink and our block of air. We can now create name sections for that. We do that in the meshing. So that's our geometry is complete. I might just delete that plane. I have no need for it. I might rename this solid as fluid. And we're done in the geometry. Now we're going to add a fluent project over here. Sorry, that's not what I wanted, that one. Delete that. We want it from up here. Fluent, that's the one we want there. Put that here. Now we can connect our geometry we just built up to here and open the meshing. Okay. Okay, so here's our geometry. I think that's finished loading. We can see clearly we have a heatsink Okay, we have a heatsink surrounded by our air there. That's what we want. We can have a look into here. One's called heatsink and one's fluid. That's fine. If we hide our heatsink, we can see that we've got a nice interface in there. That's terrific. We show body again. Meshing, I'm going to make again very simple for the purpose of this video. Just going to mesh it with an element size of 1 millimeter. Okay, that looks pretty good. Now name sections, highlight, hold control, highlight that surface, control that surface and that surface. We've got all 4 surfaces highlighted, right click, named section. That's our inlet. Okay, bring that down, highlight our top surface, right click, name section, outlet. Okay, bottom surfaces 1, 2, right click, name section, walls. Okay. So we're done in the meshing part. We can see our name sections, inlet, outlet, walls. Very good. And we're done in the meshing. We've got a lightning bolt here on the mesh, so we're just going to right click that and click update. Okay. Now we run setup. Double precision, parallel. My processor's got 6 cores. All right, Evan's loaded in. We want transient, pressure-based, absolute, gravity. Gravity, as we've seen before, is in the negative Z direction. There's our heatsink underneath there. Negative Z direction of gravity, negative 9.81. Yep, I usually change the units here to temperature Celsius. Close. Okay, models. We're going to have the energy equation turned on. We're going to look at our materials. We have a fluid and a solid. The fluid is air and the solid is aluminium. I think the project requires stainless steel solid. That can be changed. Well, I won't cover the changing of that in this video, but we can go fluid, air. We want to double click air. Let's open this here. We want to look at our density and change that to an incompressible ideal gas. Change and create. Make sure that takes effect. Close. I'm going to reopen that to make sure. Yep, incompressible ideal gas. That's good. Close. Cell zone conditions. Right, we have our fluid and our heat sink. Operating conditions, specified operating density. That's all you need to click there. Okay. As our heat sink, it's aluminium at the moment. Again, that can be stainless steel. Our fluid is air. Boundary conditions. Right, so boundary conditions, we want to select our inlet. It's a velocity inlet. We want that to be a pressure inlet. And we want to collect the thermal tab and change that to 23 degrees. Okay, so we have a pressure inlet that's set to 23 degrees. Outlet, pressure outlet, we can double click that outlet and also select 23 degrees. So that is 23 degrees external to our fluid. So if we have any air coming in, it'll be 23 degrees. From our outlet. So out of the outlet we have 23, and coming into the inlet we have 23 also. So if we have any backflow of air coming through the outlet, that will also be 23 degrees. That's that set. Mesh interfaces, we have a contact region. We want to make that a coupled interface. Okay, so contact region selected are highlighted, and these two are highlighted. Coupled wall apply. Close. We're coupled. Very good. Methods. I use simple. You can use coupled here. It shouldn't change the success rate of your simulation, but simple is a lot faster if you've got a heavy, a lot of elements in your mesh and a complex geometry. Simple can make the calculation speed faster. Coupled, is probably more accurate, but takes about 3 to 4 times as long to simulate. I'm just going to stick with simple here. Pressure, we use body force weighted, and that's the method set up. Now, calculation activities, I won't go into that. You know how to do that. You should know how to do that. Medi's shown you guys how to do that with create. Not that one. Not that one. Must be in the create solution data export. And select, CDAT for CFD post. I believe it's that one. I'm not sure, but Medi's he explains that already to you guys, so we'll forget about that. Initialization, I've always used standard. Hybrid for me creates problems and fails to converge to the necessary tolerance that the hybrid requires, so I just use a standard initialization. We'll initialize that. Patch in our temperature for our heat sink to be 160 degrees. Patch and close. Run calculation. So here, this is up to you how many time steps you want, the time step size. I recommend at least like a maximum of 0.5 second time step. That could be smaller. That'd affect computational time as well, and how long of a simulation you want. So at half a second, number of time steps 100, we're going to get 50 seconds of data. Max iterations, usually up that a little bit. It'll relax. It'll use the maximum iterations to start with, and then once it starts achieving convergence, it'll automatically drop that iterations down lower. So don't be concerned that this is going to vastly increase your computational time. It will in the initial points of the simulation, but it'll automatically relax that iteration depending on how fast it's achieving convergence. And having a higher iteration initially should make it achieve convergence sooner, which may result in less computational time overall. So I'm going to set that at 30 to start. we're looking all good here. Okay, so that calculation started. Now this is the important part here we want to look at, is this residuals of the calculation. I can see straight away it's looking pretty good. Everything's trending downwards. Specifically my energy is trending down. That's what I want to see. More often than not, you'll see your energy trending upwards. If there's problems, more often than not, you'll see your energy trend upwards and your continuity will trend upwards. That's usually a bad sign. We've hit our first time step, it bumps up a little bit, it comes back down, and it looks under control. And now, that's what you'd want to see. So I might let it hit the next time step and click stop at the end of time step. So I'm going to click stop at the end of time step right now. Okay, so we have 1 second of data, I believe. We have 2 time steps complete, 1 second of data. I might close out of this. Now, usually at this point, you would put in a results here, open the results and load the files that you saved in the location that you decided in the solution step. But right here, I just have two time steps that are solved. I'm just going to open it here just to check the if our simulation worked. Okay, load it into results. Going to make a volume render for temperature, range global, resolution 30, apply. Okay, that looks good. We can see in 3 dimensions we've got our inlet is right. We have air coming in. We can see that by the narrowing of the heat region of air, that we have air coming in from all 4 sides, compressing that heat zone of air in the 2 directions. And that's what we'd expect. So our simulation's working, our parameters are set, our interface is good. Happy days. Now you can run a longer simulation, adjust the time steps as necessary, and be confident that that simulation is going to run.